Right. So we are going to do a continue something new, but it does continue off of our lesson of simple and compound interest. So let me set up the time value of money for you. Essentially, what we're looking at is if I have $100 today, should I invest it because I can do something else with it, right? Or spend it or buy something. What is that $100 really going to be in say like 10, 20 years or even next year? How, like, because value of money changes, and it also, with inflation and just that opportunity cost of not having it available, $100 today is not the same amount that it is tomorrow, and vice versa. And so that's what we're going to look at, because people are going to come at you with all kinds of opportunities. And it's really going to be to your benefit to know whether or not those opportunities are good. So we're going to do some rather intensive math. And if you have a calculator, financial calculator, and I'm sure you can probably look one up online these days, or you're good with Excel, use them. Um, like everything else, do the math once by hand so you get a feel for it. But really, no one's going to pay you to do an equation for an hour. Now, if you are using a calculator, read the instructions. How you input some of these financial equations or formulas are dependent on the order on how you put them, depending on the calculator. So you're going to have to read the instruction manual. But I guarantee you it's going to be a lot easier than doing it by hand. So let's start off by talking about the future value of a single amount. And you're already familiar with this. So suppose you want to invest $100 at 5% interest compounded annually. We talked about compound interest. At the end of 1 year, your investment would be worth. So we're not compounding. We're just figuring out on this first year, and that's relatively simple math. So now we kind of just do that, and we have $105. Now we're going to compound it, but we're still doing the math for simple interest. We're just doing the second year on it. It's now $105 as our principal. So now we have $110.25. So we can break down compound interest into yearly components, so we can get a good idea of what we're doing year to year. So you already know this. The future value is equal to the present value, which is also the principal, times the quantity of one plus the interest rate. So we've done that already in when we covered simple and compound interest. It's the same idea. And if we're doing multiple periods, that's compound interest, we do it to the power of the time value. So if we want to know how much something is going to be worth or not worth, if what the value of it. So that's kind of the difference of what we're looking at with future and present value. When we're just looking at straight interest, we're looking at the value, and value as far as the numerical value. What is the number this turns out to be? When we're looking at future and present values, what is it worth? Because again, through the passage of time or going back in time, $100 now is not the same as $100 in the future. So again, we kind of just go through our formula here. If we invest 1,000 at 7% interest for 18 years, we set up our formula. We replace principal. We replace P with 1,000. We do the quantity of 1 plus 0.07, which is 1.07 to the power of 18. This is why we want to use a calculator. 1.07 times 1.07 times. It's if you're doing it by hand, that's a lot of paper. And so we want to go ahead and get a good feel on a financial calculator. So here what we're looking at is we're looking at a graph, and this is kind of the why who cares. And what we see here are the results, future value of $100 at a different period of interest. And if you were just to tell me, like, the difference between 10% and 16% really doesn't sound big, but we can see on the graph that there's actually a significant difference. And one of the reasons is that exponent in the formula. So remember, exponents make things grow more quickly. And so the exponent over periods is going to have a big factor. And then just the fact that it's going, even though the difference between 10 and 16 doesn't seem a lot, it's really going to amplify it. And you can see that by the time you're doing it by 20 periods, you see that effect and the big difference in that. So we're still talking about this present value of a single amount. So when we do calculate a present value, we can, or when we're calculating a future value, we can go in the other direction. And we call that calculating the present value. And it's just the reverse or the inverse of compounding. We call it discounting. And when we discount, so if we think about the formula, we're multiplying by a quantity. So remember, mathematics is all about balance. And when we're doing our equations, how do we negate multiplication? We divide. So if we know the future value and we use division, we can come up with the present value. And so the formula looks more like this. What if we had in the future, like we're trying to figure out how much that would be worth in the present. How much is $1,000 at 6% worth 5 years from now? Or backwards, like how much will that be? Someone's promising you so much money, and you're like, okay, how much is my $1,000 worth now? And so now we switch the formula, and you can do I'd be really impressed if you do the arithmetic to change the equation on this, but this is the formula. And really, so now in the present, we have $747 that will grow into $1,000 in 5 years at the 6%. So we could go backwards and forwards. You can always algebraically rearrange your formulas so that you can find out what it is you want. And just keep in mind that that whole nature of math of being a balancing act. So this is just another graph to show you how the present value going from future value to present value works in inverse. So a future value of an annuity. So an ordinary annuity, wrong word, annuity, is being paid out a specific amount of money at a specific amount of time. So this happens, and you might pay into an annuity so that when you retire, you're still getting a paycheck. You're getting a certain amount at certain intervals. So if you're investing $100 at the end of every year for the next 3 years, and you're getting 8% per year on that investment, you can calculate how much you would have at the end of the year, and that would be the money you would be getting back. And we go ahead and use our formula, and here we're doing 0, 1, 2. So the future value of this annuity is $324.64. So that's a lot better than 100. So you might say, yeah, I'll take that annuity. And we can just see the math going in the compound way of how much we're getting per period. So the exponents are the periods that we're going to represent in N when we use a formula. So let's talk about this formula and what makes it up. So we've seen this before, 1 plus I. So 1 plus the interest rate, and that one's pretty easy, just smush it together because we're just adding. We're doing the number of periods is going to be our exponent. That's going to be the large factor of how big our number is going to get. And why more than likely we're going to want to use a calculator. We take that answer and subtract 1. And then we're going to divide it by I. And this, again, useful when using a non-financial calculator. I would work it out once and then just use a financial calculator or Excel. So when we're doing a future value of annuity, we can take a look. So remember, P is going to be the thousands, going to be how much we invest, the principal. At the end of each year for the next 12 years, that's going to be our N is going to be 12. We're earning 14% per year. How much would you have at the end of the 12 years? And so we just go through. We're doing the future value of 12. So that's all that indicates there. That's what that means. And we're ending up with 27,271. So suppose you can invest a project that will return $100 at the end of each year for the next 3 years. How much should you be willing to invest today, given you wish to earn an 8% annual rate of return of investment? Now that sounds very convoluted, but remember, we're discounting backwards, so it's the same thing. We can just plug into our formulas the different values, and as we just work that through each one, we come up with our present value of 257.70, and then we make a decision: is it worth me investing 257.70 to get that return of $300 at the end of each year? So in the present value of annuity, remember, present value, we're usually trying to figure out what's going on now. We're using the same formula. So this is given that interest is 9%, and we're doing 20 numbers of periods times 500,000. So why is it 500,000 when they're telling us 10 million? And we're ignoring the taxes. And you're not here, so you're not answering, but I'm going to pretend that you, or actually ask me in the next class, and we're going to discuss that. So just to kind of go over, we've talked about future value of a single amount, the present value of a single amount, the future value of an annuity, and the present value of an annuity. This is how we go back and forth between knowing whether our money today, what's it going to be worth in the future, or whether it's based on our assumptions for the amount in the future, whether it's worthy for us to invest our amount today. And so these are the different formulas you can use to value that. So in addition to using what we already know, remember, we can always switch these formulas around to figure out the different components using algebra. We can solve for the interest rate. We can solve for the number of periods, how much the annuity amounts are, dealing with uneven cash flows. And that's, what if I'm getting $300 one year, 200 another, 10,000 another? We can still use these formulas to figure that out, and how to amortize loans. So in an amortization chart, how much do I owe with every payment? And if I'm making certain payments, how much do I owe after that? And that's very much like the uneven cash flow concept. So I do want to mention about an annuity due. So I don't know if you picked up on it, but in the other examples, we were always talking about the end of a period. An annuity due means the beginning of the period. So that changes the number of periods, because in an ordinary annuity, say like I owe you on December 31st, haven't paid that out yet, so we don't count that period. In annuity due, 1st of December. So I may have put that. So it affects the numbers of periods in that. That's just something to pay attention to. So it just changes the number of periods in your formula. Annuity due, beginning. Ordinary annuity, at the end. And then when we're looking, there's a thing called perpetuity. And there are a lot of financial products that leverage this. In reality, they're counting on you dying sooner than planned. Hey, we're going to pay you $100 for the rest of your life. Well, they're kind of counting that you get hit by a car next week, so they don't have to pay you. When we're doing this, the present value of that payment, whatever it is they're doing, is going to be the payment in perpetuity divided by interest. And then there's non-annual periods. So it's just something you have to pay attention to when we're thinking about periods. So I know when we were talking about interest, APR is always based on the annual period. But sometimes we've got to break it up into other amounts, whether we're paying semi-annual. So here's the example. Are we paying annually, semi-annually, quarterly, daily? And so we have to divide it up. So annually, semi-annually, that means twice a year. So we're gonna break that down into two, quarterly by 4, daily 365 is how we're gonna break that up. Do not, before we talk about this, do not hesitate to use your fingers to count. I know many of the accountants that uses their fingers to break up and make sure periods are the correct amount, including myself. So an effective annual rate it's just another metric. You'll hear this a lot with, especially like tax rate, what the effective rate is. And this is the formula. Yes, it looks ugly, but again, we can break it down pretty simply. ERA is just the name of effective annual rate. That's just what we're trying to solve for. And the formula is the quantity of 1 plus I num, which is the quoted annual rate, divided by the number of periods in the year, right? So M, nothing really complicated in there. Then we're going to take that to the power of the same number of periods minus 1. So again, if this ever shows up, or any formula, we don't need to freak out. We just need to start replacing some of that stuff that scares us with the values we're given so that we can start breaking it down. And even if there is something that we find missing, we can more likely solve for that. So that's all I have here for future present value. I will say, back in my day, we had to do this with charts. I still think even in college level, they'll teach it with charts. Use your financial calculator. Interesting to me, trivia is that those charts we use, some dead smart guy a long time ago, and I know we haven't done calculus, but there's this thing called an integral. So once we do calculus, we balance it out because we're doing math, so we always have a balance. The opposite direction is called an integral. They're not that easy a lot of times. So this dead smart guy figured out all the integrals which help us solve for future values to like a fifth decimal point. And he made these charts that are still used today. But we have calculators, we have Excel. Use them, learn them, and use them. It'll make and save them. If you're using Excel sheets, save them. I still have tons of calculators I've built. And now I don't have to do the math. I just pop them in, use them all the time. So I will talk to you soon. Enjoy your formulas. They're fun. They are.